So welcome to Kotlin variance modifiers and covariant nothing object pattern. A little long name, but it pretty well describes what will be covered in here. Generic type modifiers, covariant nothing object, variance limitations. Thing that you are probably all using, and very little people know how does it really work. And I hope that after this presentation, you will pretty well understand variance modifier, so the essence of generics, maybe not the essence, but the hard part of generics. And you will also understand the covariant nothing object that is used quite widely, not only on our projects, but also in standard library and many objects that you use, like arrow. So let's start with a very short slide about myself. I am Marcin Moskala, an author of a couple of books, including Effective Kotlin, Kotlin Coroutines, Kotlin Essential, Functional Kotlin, and Advanced Kotlin. I'm also teaching Kotlin, and this presentation is based on a part of my workshop. Workshop's name is Kotlin for Developers. You can find it on KT Academy. So what I'm telling you right now is a part of my regular workshop. I also explained that in the book Advanced Kotlin. And a small announcement of today is that this book can be finally considered finished. Will be available on Amazon during the weekend or during the next week. And right now, on LeanPub, you can consider it finished. So let's start from generic variance modifiers. At this point, I assume that you know the essential of generics, so that you know that you can define a generic function, so a function with a type parameter. When you call it, you specify type argument. Type parameter is a placeholder for a type, and whenever you use it during runtime, during compilation, type argument will be used at the place of type parameter. There are also generic classes, so this T in the angle brackets is a type parameter. That is a placeholder for a type. When you create an instance of this class, you specify type argument, so a specific type that will be used, and you can referencing it using type parameter name. I hope it is all clear. What seems to not be clear for the majority of developers is the variance modifiers. So invariance, covariance, and contravariance. So in and out, in and out. How does it work? The idea is very simple. Variance modifier decide what is the relationship between boxed types. So consider that you have a generic class named box. Okay? The question is, what is the relationship between different boxes? So if a number is a supertype of int, yeah, number is all the numbers, yeah, double, int, long, etc. So if a number is a supertype of an int, what is the relationship between box of number and box of int? And the answer to that depends on the variance modifiers. The default option is invariance, meaning there is no relationship whatsoever. But if you use out modifier, you are dealing with covariance. And contravariance, the in modifier, is the opposite. So if number is a supertype of int, then box of number is a subtype of box of int, the reverse relationship. This is where I could stop my explanation, but you likely need some examples. Let's start with a few hierarchies. Here I have a hierarchy of objects, puppy, hound, dog, etc. And a hierarchy of boxed variants of those objects, or box of puppy, box of hound, dog, etc. And since we are dealing with invariance by default, there is no modifier whatsoever. There is no relationship between those boxes. Yeah? So in practice, you cannot use box of puppy where box of dog is expected, and you cannot use box of dog where box of puppy is expected. Yeah, the default behavior. Now, if you use out modifier, there is the same relationship between boxes as there is between row types. Yeah? So box of puppy is a subtype of box of dog, meaning that in practice, you can use box of puppy as a box of dog, but not the other way around. OK, that's essentially the explanation of covariance. And the opposite contravariance in modifier reverses this relationship. Notice that the arrows now are pointing on the opposite direction. So box of puppy is a super type of box of dog. So in practice, you can use box of dog where box of puppy is expected, but not the other way around. OK? I guess this helps you a little bit, but this is likely still confusing. So let's show you some practical examples. How this can be useful, and especially you are likely considering how contravariance can be useful because it looks like an absolute madness. But let's start with a very simple example. Consider that you have animals, and among those animals, you have cats. So you made a function to pet all your animals when you are coming back home. Apparently, you came back home, and you can only see cats. So you have a list of cats. So the question is, can I use list of cats where a list of animal is expected? Can I? Yes, I can. I can. And why can I do that? Yeah, because list is covariant, yes? Out modifier. List is covariant because it is representing a read-only list. This code wouldn't work in Java for two reasons. Like, the more important one is that in Java, there are no variance modifiers, so you couldn't do that. But second of all, in Java, you do not have a concept of read-only list. There is only a list which is a mutable list. Yeah? And you couldn't be able to do that for a mutable list. You will see that clearly later. But list is covariant because it can only be expressed out, read out. But mutable list is invariant. So you cannot use a mutable list as an argument where a different type is expected. There is a very good reason behind it. Because if I would be able to do that with a mutable list, then in here I could add an animal which is not a cat into my list of cats. And then here I could expect a cat at the last position, and kaboom, I would have a dog where I expect a cat. So this is why it works for this casting works for a list. List is covariant, but mutable list is invariant. OK? So this is our list example. That's just the beginning of all the fun. Another example that will be a hypothetical project of yours. Imagine that you have a sender of messages, the interface to send messages of a certain type. And you have different types of messages, like order manager messages and invoice manager messages. Now, you decided to implement a general sender. So a sender that is capable of sending all kinds of messages. Yeah? It's a sender of message. But you want to use this, like limit what people can send by upcasting your general sender into a sender of specific messages, like order manager message or invoice manager messages. Can you do that? Can you do that? No, the answer is no, because here general sender represents a sender of message, yeah? But here we are expecting a sender of order manager message. So what can we do to make it work? Contravariance. In this case, we need to have a contravariance, so the in modifier. In modifier is used for consumers, for things that are coming in, consuming inside, and it is appropriate for this type. This sender consumes messages, and a sender that consumes all the messages can be freely upcasted to a sender that consumes a specific kind of messages. This is what contravariance is for. You will see that more clearly once we analyze other examples. Does that make sense so far? OK. So let's move into another example from what is built into Kotlin. Imagine that I have this function that is transforming an integer into anything. I just am feeding that with integers, and I'm printing the result. Yeah? So it's a function from int to any nullable. So I should provide a lambda expression of this type for it. But I left it in another jacket. But under my hand, I have a different function, a function that transforms an integer into an integer. And the question is, can I use a function type from integer to integer, where a function type from integer to any nullable is expected intuitively? I mean, if you think about that, it kind of makes sense, yeah? So if we are feeding it with integer, that's fine, it's expecting an integer. This is returning an int. We expect it to return any. Everything is fine here. It will work fine, OK? Another example, function from number to double. Do you think it will work or not? I mean, intuitively speaking, it is also kind of fine, because we will feed this function with an integer. It expects a number. Integer is a number. It produces double. We expect any. That's fine. It will work fine. And another example from any to string, intuitively speaking. Again, we are feeding it with int. It expects any. That's fine. It produces a string. We expect any. It will work fine. We don't need to think about that to use it. It's very likely that you've been using some references, and oh, that's work. Nice. It looks like a Kotlin magic. But it is not. You don't need to think what's the reason behind that. You just need to know it is that function type have some flexibility, which makes our development process easier. But if you are interested in why does it happen this way, the reason is that the type parameters of function types have appropriate variance modifiers, yeah? In and out. Parameters are in, result is out. That's why you can draw this example hierarchy of types. You can see that a function from int to number is a subtype of a function from int to any. And if you start at the top and go slowly down into the types, you will see that you are going from more specific into less specific type. Yeah? So from int to number to any. And if you look at the result type, you go from the less specific type into more specific, like any, number, and int. Yeah, clearly, for type parameters, we have the parameter types of this type, function type. We have contravariance, so in modifier. For the result type, we have out, so covariance. OK. This leads me to a pretty popular pattern that you can find in many libraries. You can also, I could also find it in a code base of different projects, commercial projects. But I never found a name for that, so I named it myself. This is my author name, Covariant Nothing Object and Covariant Nothing Class. Let's explain that step by step. So imagine that you have a small hierarchy of messages, and some messages keep some data, so it's appropriate that those are classes. But some messages do not keep data. And Kotlin will suggest you that in such case, you should not use a class and create a new instance every time you use it. Instead, you should use an object declaration and have one instance for all the messages of this type. Yeah, this is a low-level optimization. From the fact we are using object keyword there will be only one object, singleton object, instead of multiple objects representing this message type. Yeah? And the same pattern can be applied when you have generic classes as well. Consider a situation where you have a linked list. Linked list is a data structure that has either a node, which has a value and reference to the next part, or an empty, which is representing the end of the list, or an empty list. So you can create a list from a couple of nodes, node with 1, referencing to node with 2, referencing to node with 3, and then empty. And in here, we need to create a new empty object every time we want to create the end of this list or create an empty list, what is clearly not optimal for us. We need to, probably in our program, if we would need to use this data structure, we would need to use it quite often. So how can we improve that? The pattern is pretty simple. This is a covariant nothing object. We turn empty into an object. But since we need to provide something as a type parameter in here, we use nothing type. Nothing is a subtype of all the type. And we also need to make linked list covariant, yes? So out modifier. When you do that, linked list of nothing is a subtype of all the lists, on all the linked lists, yeah? Because nothing is a subtype of all the types, so linked list of nothing is a subtype of all linked lists because we are dealing with covariance. So you can reuse the same empty object in all the places where you're using it. Okay, that's the pattern. This pattern is used in many places. I will show you an example from standard library, something that you are probably using many times every day. If you consider list of, this is a function creating an empty list. As you can see, it creates an empty list. But you might not have ever considered that whenever you create an empty list, you are always using the same list. It's literally only one list representing an empty list. It's reused everywhere in your project, yes? Instead of creating thousands of empty lists, because empty list is a pretty common thing to use, we have only one. And this empty list is, of course, an internal object of Kotlin standard library. And what a surprise, you can see it is a list of nothing, yes? So thanks to the fact it is a list of nothing, it is a subtype of all the lists. So the same object can be reused everywhere. That is a nice optimization used for collections. You can check it out yourself. Another example comes from an internal library we created for one company. Do not say too much. The library was to schedule tasks, to schedule tasks using Mongo database. And task scheduler has a different kinds of properties. For the sake of our example, let's assume it has name, data, schedule that, and repeat every. The details doesn't matter, but it is a nice example. And at some point, we needed to introduce a way to modify those tasks. But we didn't want, we wanted to have an object that is representing an update. So this update can be pushed through the library for a couple of layers and used there. So we wanted to have a nice way to express what should be changed in an object. And a classic Java approach would be to just make nullable properties, and null should mean a lack of change. So this is not a good approach. First of all, you have only one null. So if you have a nullable property like data in here, you do not have a way to express, hey, I want to change it to null. Yeah? Second of all, it's not very type safe. It is quite messy. And also, there is no way to express different kinds of messages. So what if you want to say not change to something or not do anything, but also set default or set from somewhere else? Yeah? And for that, Covariant Nothing object is very useful. So this is a lot of code, but it's not very complicated. With Covariant Nothing object, you can make, maybe I will make it step by step. You can define a hierarchy. Let's start with this one, of how property should be updated. Okay? And this is a sealed interface, so a closed hierarchy that can express either keep or change to. And in your update task, by default, you are expressing, hey, I want to keep them all. But a user can easily express this update, which is, for some properties, keep it. For other properties, change to something else. Okay? It is type safe. It is not blocking us at all with any kinds of messages. We can easily add a different kind of message, like, I don't know, restore default, or maybe set default. We can make a bigger hierarchy so that for some properties you can set default, and for other properties you cannot set default. This is a nice pattern used in different places. Or sometimes it is like not set and set. In some other places, these kinds of messages are expressed. So here I have a bigger hierarchy where you have tasks that have default, and they have additional message set default, and tasks that do not have default, and for them you can only set keep or change to. Does it make sense? Okay. The next example comes from Arrow library. This is not the actual code. I will show a better code later. So you might know it or not, but in Arrow library, there is this type either that expresses an alternative, that it is either that or that, yeah? either that of this type or that of this type. And a very naive implementation of this pattern could look as follows. Yeah? We have either, which is either left or either right. So this implementation is not very good. Why is it so? Do I have main commented? Why is it so? So consider the following code samples. So first of all, I would want to create left. This is already with nothing here. If there will be left and right in here, that would be very problematic for me, because I wouldn't be able to create left without specifying right type. That is, not very good. That would be very problematic. So I replaced this type with nothing, but this still doesn't work. the point is that we want left of some type to be independent from right of different type. They should not know about each other types. And the only way to achieve that is, of course, to use nothing in here, but also to use contravariance, which is appropriate because it's a read-only type, read-only class. So covariance, the out modifier, is appropriate. Only with this covariance and nothing type, you can create left without specifying right type, or right without specifying left type. And only then, left, which is of type error, can be used both as either of error and int, as well as, I don't know, error and string or whatever else. I hope you see the idea. It's more or less the same idea as before, but a bit more general. And this is a pattern that I call covariant nothing class. OK. I had the slides that are showing that, like either LNR. It's very limiting because you cannot create right or left without specifying type for the other side. If you use nothing, then you cannot create that because you would need to have nothing here and here, and only covariance help us. Also notice that covariance must be both in either and in left and right, because they have the same name, but those are different parameters. And their variance is independent from each other. So for instance, if I wouldn't have out in here, that would work, but that doesn't work. Like left error, like left of error, wouldn't be upcasted to left of throwable or left of any. Okay, so they are independent. Though. Those type parameters have independent variance. Okay, what leads us to the last section of this presentation? Limitations. Of course, with great power comes great responsibility. So when we have a nice tool that allows us to do different things, for our own safety, there are some limitations. And the fun fact is that those limitations teach us a lot about use cases of those variance modifiers, because they are blocking what is not safe, so leaving what is what they are supposed to be used for. For instance, I want to start with a small Java example that will show us why do we have those limitations. So those are 3 Java lines that can break your code without any warning. At least the last time I checked, there was no warning. Okay? What's going on in here? In here, in Java, we are creating an array of type integer, array of integers, and we are upcasting it into array of objects. In Java, there are no variance modifiers, and there is only one type that is covariant, and this type is array. What is a little bit sarcastical, because this is a type that should not be covariant, and arrays in Kotlin are invariant. They are not covariant. Okay? They have no modifier. But in Java, they have out modifier. You can imagine that. So array of integers can be upcasted to array of objects. Then you can set on some of its positions a string or whatever else. And kaboom, exception in thread array storage exception. Yeah? This shows us a problem with variance modifiers. To understand this problem, we need to understand the difference between in positions and out positions. So in position is a parameter type. Everything that comes in, yeah? Dog comes into the function. It is an in position. And fun fact about in position is that you can upcast to an in position. So where you expect a dog, you can provide a puppy, hound, everything that is below the dog, yes? When we are dealing with out position, oh, sorry, I will have that later. OK, so in position does not like itself with covariance, because it allows us to upcast things from the bottom, and covariance allows us to upcast objects, so objects can go out, and then in position can take it from everywhere. Yeah. Maybe this will be a bit more visual. Imagine that I made a box for a dog. I can upcast it to a box of animal, and I can put anything from below animal, like a human. Of course, a human will not fit into a box for a dog. Kaboom! We would have an exception if it wouldn't be prohibited. It is prohibited. When you are using out modifier, so covariance, you cannot allow in positions. You can only allow out positions. Like the name suggests, out allows out positions, exposing something. Yeah? This type parameter cannot be at in positions unless they are private. Private is fine because inside of a class, the type is already set. So casting cannot happen. Everything is fine. So private, fine. But out types, covariant types, can only be expressed on out positions. Does that make sense? You can generalize it further, yeah? I could use a box of, I don't know, int, upcast it to a box of any, and put, I don't know, a string, whatever. The idea is that in the type hierarchy, I can upcast box up, and in can take everything from below. So some things that we shouldn't be able to put there. Notice that there is a completely different story about out position. Out is what is expressed outside, so the result types. And notice that we are also dealing with upcasting, but since we are on the other side of the function, when you have a dog returned, we can upcast it to everything that is above it, yeah? So wild, animal, any. So even though it's still upcasting, we can upcast it to everything that is above that. And now, the out modifier, the covariance, like itself with out modifiers, because it's the same relationship of casting, yeah? From box of, let's say, nothing, we upcast to something upper, like a box of int, and the result type can only be upcasted upper, what will still be above what we started with. So everything is fine with covariance and out position, out modifier and out position. However, with out position, we have the reverse problem, or co-problem, for functional developers here, when we are thinking about the contravariance, the reverse relationship, yeah? It's like in a mirror. It's like the same problem, but in a mirror, you know? So right now, box with an animal can be upcasted to a box of a dog, because we are dealing with contravariance, so reverse relationship, yeah? Box of animal is a subtype of box of dog. And if I would use get on this box, I could expect it to be, let's say, wild. You know, animal and wild has no relationship, but dog is both animal and wild. I don't even need to do that. You know, even if I would try to get dog, I would fail, okay? Because it's animal, not a dog. So this just cannot work for the same reasons. So this would fail, and to prevent such situation, it is illegal to use contravariant, so in modifier type parameters on public out position. So in is for things that are coming in. I hope you can already see the picture. Out is for things that are going out. Yeah? Like list is the good example. Everything that is immutable, like list, either, everything. In is for things that are coming in. Yeah, so if for instance, I'm improvising a bit now, but if you are into coroutines, if you are using continuation is consuming things, yeah? This resume with is an in modifier. So of course the continuation type is in, yeah, because this type is only coming in. If you are into, let's say, property delegation, there are those interfaces, read-only property and read-write property. And in read-only property, T is only coming in, so it is in modifier. And the V is only coming out, so it is having out modifier. While on the read-write property, V is both in and out, so it has no modifier. Quite straightforward. That's why those names in and out are amazing and super intuitive if you think about that. OK, and as I mentioned already, contravariant types, type parameters, so in modifier cannot be expressed outside unless on private functions. On private, everything is fine, because inside an object, the type is already set. But you cannot have it in public out position. Now, we have a saying in Poland that rules exist so that we can break it. And every good rule should have exceptions. And this rule has exceptions as well. And the most popular exception can be found in the interface that you learned about already, in the list interface. You see, you already know that list is covariant, yeah? Meaning that its type parameter can be only present at out position. And everything is fine, except for function contains, and function contains all. Yeah? Pretty clearly, if you think about that, here we are expecting int. And int is here because this is a list of int. And so you might be wondering, how the hell is that possible? And the answer is pretty simple. There is this annotation, unsafe variance, that is literally turning off these limitations. So with that, we can do absolutely everything you want. But, well, beware. OK, that was everything. Everything is described in bigger detail in my book. It's officially finished. It will be published on Amazon next week. I also teach that, there should be Kotlin for developers. There is a different variant for Android developers. Right now, I'm doing both Android and backend, so I provide both workshops. And there is also a dedicated workshop, Advanced Kotlin, if you are interested on only advanced things, like only KSP, reflection, and variance modifiers, contracts, and this stuff. I also have a dedicated workshop at KT Academy. If you have any questions, like right now is a good time, the next good time is today outside. I will be around, but today I'm not going to be here. Tomorrow, work is calling me. That was everything from my side. Thank you for your attention, and have a happy Kotlin.